the introduction, and thank you very much to the Academy for inviting me. It's a great honor. Uh, I'm a marine geophysicist. What I basically do is, with the help of sonars, study how the seabed looks like. As the previous speaker, Professor Atmanan said, we don't know much about the ocean or how the ocean bottom looks like. So it's actually an excellent follow-up talk. Now, he talked about how we had to monitor the uh, waters, ocean waters, where now I'm diving deeper and onto the seabed and show you what it looks like and what are the benefits out of it and what are the potential, some hazards, potential hazards. It can be a hazard, but it's kind of talking like a futuristic way. What could be any hazards like tsunamis or landslides or things like that. So first of all, to just introduce everybody to what is an exclusive economic zone. So here you are looking at the tide line where you have the beach, and from there, the low tide line, you take 200 nautical miles out into the sea, and that is the exclusive economic zone of any country. And within that waters, any country has its right to explore and exploit any resources within the water, that is fish or any other like wind energy or wave energy. Or you can also go to the seabed and actually see if there are oil or gas, minerals. So any country has its own right to exploit that. So we classify the seabed in different terminology. We don't usually say economic zone. We usually say like, okay, you have a continental shelf, that is the shallowest part out of any, and then the depth suddenly start to increase much more rapidly, which we call a continental slope. And then you have a continental rise, which is where it flattens out, and then you have the deep seabed. So India has the 18th largest economic zone in the world. You can see here on the map. I think that this pointer is a bit shady. Yeah. So here you can see this is basically 200 nautical miles out of the coast of India. But where it shares, when there are other countries nearby, then usually you kind of agree to a central line, nearly equidistant between each country. Sometimes it can be controversial, but more or less they agree to a particular line. So you can see India shares its economic zone with many countries: Pakistan, Maldives, Sri Lanka, Myanmar, Thailand, Bangladesh. So it's quite large, nearly over 2 million square kilometers. Why do we need to map the EZ? Mapping the EZ here, I particularly mean how the EZ looks like, what the seabed looks like, what is there in the seabed. Because it's important to know if there are any potential resources and how to manage them, and also to navigate these waters. And if you want to construct something like, for example, a platform, soil platform, and also if there are any geohazards, if there are potential for earthquakes, or if there are potential for landslides, things like that. The major applications to the common public involves the fishing operations. We can benefit from such mapping and mineral resources, oil and gas, and also laying of pipelines and communication cables, and also construction of near port or near port construction. But scientifically, when we look at it, you have different focus. You can look at the seafloor morphology and how it looks like, what are there. And you can also understand about the sedimentation history, how the rivers have controlled the sediment output into the ocean over the past. You can study how the life looks like under the ocean. You can also look at how the Indian margin has developed over the years and how it's going to develop in the future. Also look at how climate has changed. You can sample the sediments on the seafloor and then actually reconstruct how the climate looked like in the past and how it will, based on that, you can try to predict how it will look like in the future. And then another key aspect is a geohazard, where how the processes occurring in the ocean can have an impact on the human, for humans and also human-made objects. So with these objectives in mind, the Ministry of Earth Science and Government of India launched this program known as the Geoscientific Studies of India. So its main objective is to create a seabed topographic map of the economic zone of India, and also put them together in a database which can be accessed, which can be accessible to everyone. And additional scientific objectives involve evaluating the geosat potential and also to understand sedimentation history and paleoclimate in the of the Indian Peninsula. So this is a long-running program. It's still ongoing. It's not complete, and it's started way back in 2003-4. That is when it was initiated. So it's been running for nearly 20 years, and it's an ongoing program. And NCPOR, the National Center for Polar and Ocean Research, is the nodal agency for mapping the Indian Ocean, along with these three other institutes: National Institute of Oceanography in Goa, and the National Institute of Ocean Technology in Chennai, and Geological Survey of India in Bangalore. So we are conducting these surveys in two phases, where the phase one survey takes a deep water surveys where it's below or deeper than 500-meter water depth. That is NCPOR is handling, and phase two, where the shallow water surveys, that is near coast areas below 500-meter water depth. That's taken care of mostly by NIOT and NNA. How do we go about mapping this? So you essentially need a platform, which is usually a research vessel. So we use multiple research vessels. These are Indian research vessels, or the Sagar Kanya and Sagar Nidhi. These are operated by the Ministry of Earth Sciences. And sometimes it's very hard to get time on this, dedicated time, because these are always so busy with a lot of different objectives and a lot of different institutions vying for the time. So we sometimes have to charge foreign vessels, such as these vessels, Boris Petrov and MJ Sagar. So we usually have to take these out into the sea for months on end and survey the waters. And what we say by mapping or surveying, here it's mainly acoustic surveys, basically a multi-beam echo sounder. That is a sonar, basically. It's very simple. It's attached to the hull of the ship, which sends acoustic pulse, and then it measures how long it takes to come back. And then if you know the velocity of sound in water, which is somewhere around 1470 to 1500 meters per second, then you can calculate how deep that location is. So you do this. That's sometimes you call it a single beam. You send one signal, but usually how you do this is in multi-beam echo, you have multiple beams. Usually you have 800, 900 beams going perpendicularly from the direction of the ship motion, and then it's basically sending back information over a large area of the seabed. Usually it's 3 to 4 times the water depth. So, and then we basically create maps like this kind of topographic maps where here the red is shallower and the blue is deeper. And usually this frequency range is between 10 to 500 kilohertz. That's the acoustic frequency. We also do other types of acoustic surveys known as side scan sonar, where we have a tow fish, which is basically an instrument we tow much closer to the seafloor at a higher frequency range. It kind of gives you some information of what type of sediment it is based on the reflectivity of the reflection strength of the signals. We also sometimes use a subbottom profiler, which is much lower frequency range, which also gives you some information about the few hundred meters below the sediment, how it looks like, what is it. And we also collect some samples at certain locations. It's not something we conduct all over, but at certain locations, and if the facilities are available, we also collect sediment samples using gravity cores, and also biological samples from the water column, like plankton and using the bowler. So what is the status of this program? As of now, over 90% of the deep water area, that is below 500 meters, has been covered. So the green area, that's been covered by NCPOR. You can see the western margin, the deep water area is more or less covered. Where we have still some gaps, these red areas, those are the big gaps, and also, sorry, not the red areas, the blank areas you see here, for example, of Paradeep here, and also in the Andaman coast, those are the big gaps, and also we have a bigger gap on the southern part of India. But I will focus here, I'll show you a glimpse of some of the results from these studies, and also I am focusing here now on the west coast, where we have a more complete understanding of how the seabed looks like. So it's not that we not completely know about we don't know completely about the seabed. This is a publicly available map from the general bathymetric chart of the ocean, GEPCO, it is called, released in 2020. So here you can see the western coast, you see the cities Mumbai and Cochin here, and then you see the coastline here, you have the continental shelf here, and then it suddenly gets deeper. So there's a shallower part, and then it gets deeper and deeper. The blue here represents nearly 4,000 meters. where the shallower part is usually it's less than 500 meters. So this is the publicly available data. Its resolution is 500 meters. And I will now overlay on what we are talking, and then you can see the difference. How different it is, like putting on a glass. So you can see particularly in these areas, if you look at this area, there was not much information. We don't know what it was. And then suddenly you have a very nice submarine channel complex. You see a lot of new mounds and features popping up all over in this area. So, example, some of the features what we found. The bathymetric height. These are basically underwater mountains or hills. They don't breach the surface water, so these are not islands. They are below the seabed. And I will come into more detail in the later slides on those. And then you have submarine landslides, which are basically like landslides, which are basically similar to what landslides are on land, but these are on much larger scale. And you have submarine canyons, which are basically these very narrow, steep-sided valleys, and these are basically important for the supply of sediments into the deep sea, and also very important biodiversity hotspots. And you also have submarine channels, where these are basically underwater rivers, you can say. And these are very important in terms of oil and gas and sediment supply into the deeps. So here I will focus on two particular features, that is particular highs and then the landslides, where I will try to share a bit more information. So why bathymetric highs are important? Because these are basically like underwater mountains, and it in water it affects ocean circulation as it affects air circulation, wind circulation in on land. In the ocean, it affects the circulation, and also it creates these local upwelling zones where the water is coming up and creates a very nutrient-rich water where you have very high productivity, and so usually you have a lot of animals there. So this is a very interesting area for potential fishing, and also very interesting habitats, some unique habitats as well. And also it's very crucial for safe navigation. This is an image of a submarine USS San Francisco. It hit in 2005 on an uncharted bathymetric high. It's basically a mountain, and it damaged like that. So it's very important to know what is on the seabed before you go with the submarines or anything, and then to navigate these waters. And these are also potential mineral occurrence zones. This is an example of cobalt-rich minerals which are deposited on seamounts. So there are multiple ways in which these are important. So in the western continental margin, we identified about 33 distinct bathymetric heights, which were not identified before based on this data. And these bathymetric heights are classified in different ways. Some are called the seamounts. Seamounts are usually if it is 1,000 meters above the seabed. So, but it shouldn't breach the water. So it's if it's taller than 1,000 meters, then it's called a seamount. And if it has a flat top, then you call it a guyot. If it is less than 1,000 meters, you call it a hill or a knoll. So it's kind of like how we say sometimes hill and you have a mountain, something like that. And then if it is not a seamount, so it's below 1,000 meters and it has a plateau, we call them a plateau. This is a classification by the International Hydrographic Organization. So particularly, I would like to focus on how these bathymetric heights are formed. Because undersea volcanism is the main driver. Because you can have a mantle plume sitting, and then because of the plate motion, plate tectonics, the plates are always moving. So you have a volcano forming in one area, and then after some time it moves. And this is process happening over millions of years. And then you have these extinct volcanic islands going, and the erosion and all the other activities, and it becomes a seamount. So we believe that the seamounts in the western margin is basically derived from the reunion and the Marian volcanism. Also, so the Indian plate movement over those hotspots that created these seamounts. An interesting example of such seamount is the Sagar-Kenya bathymetric complex. This we are known for some time about this particular feature, where you see three distinct bathymetric heights here, and it kind of resembles volcanic caldera, kind of collapse. So we believe it was probably a past volcano, which is in this shape now. Maybe it was much bigger in the past. The next feature I want to focus is the submarine landslides. are basically downslope movement of sediments in response to the gravitational force. So it usually occurs between the funnel shelf and funnel slope, where your slope is slightly higher, and then you have loose sediments, sometimes very water rich, and you have a lot of sediment being supplied from the land. Then it can create these sort of slides. And the major difference from the on-land landslides is that usually this runoff distance is very high. It's hundreds of kilometers in case, and the landslide scars are much bigger compared to what you see on land. And these are usually caused by earthquakes and also loading of slopes, that is heavy sedimentation here. Suddenly a lot of sediments coming in, and sometimes weak layers where they are very water rich, and sometimes also gas adit dissociation. Gas adits are materials which are basically ice-like materials which composed of water and methane. When it dissociates, releases the methane, and a lot of water is released, which kind of destabilizes the sediment. And also volcanic activities and non-fusion such landslides. This is a particularly large submarine landslide we identified off Cochin area. It's 46-kilometer wide, this slide scar, and the total length of this is about 100 and nearly 140 kilometers. That's basically distance between Mumbai and Pune, for example. And it's covers a very large area. This site deposit occupy nearly 5,700 square kilometers. And this we think is likely caused by a high sedimentation rate in this area. Another interesting one is of Kilom. It's also on the very southern part of the southern point here. You can see the location in this map here. And here it's very interesting because you see some slide deposit here if you look here, but you also see these cracks, these fault cracks. Here there's a profile across it which is about a 55 meter deep. These cracks, you can see it's a bottom profile across it, and you see some planes where it's sliding off. So we think that this is about 60-kilometer long, this track. We think that this could be a precursor to future landslide. So we have actually provided this information to, for example, INCOIs, where they can actually potentially deploy their tsunami warning buoys, for example, to if something happens. We don't know this data has been collected already nearly 10 years back. So there is no continuous monitoring because we don't have time and money to go to the same place over and over again. So we don't know how this is developing, but it's an interest area to focus on. So to summarize, basically it's a very essential, although we have been, as I saw, it's been going on for a quite long time. Over 70 expeditions have been conducted, but still there is quite a lot of area to cover, and many areas need to be resurveyed for to know what is happening, to monitor these geohazard locations. I would like to thank the Deep Sea Survey and Mapping Group where I'm from, and also particularly Bijesh and Sushant, who has been working on these data mostly. So, thank you.
To know which among the bathymetric highs contribute most significantly to bentopelagic coupling in terms of what drives the energy budgets in the deep sea. I understand that the hydrothermal vents you have exceptionally rich biodiversity. So how do you explain that in absence of sunlight?
In the hydrothermal vent case,
right?
Yeah, that is the basis of an ecosystem. There is not photosynthesis, chemosynthesis. So so you have sulfur reducing bacteria and all that, and then you have higher level organisms. So that is hydrothermal vent. Here you don't have such an energy source. So this is basically all the biodiversity is due to the upwelling of this nutrient-rich water coming up into the closer to the.
That was my first question. Yeah. Which among the bathymetric highs contribute most significantly to that coupling?
Which among means?
Given a list of five.
Yeah. So usually it is not which type of this is actually contributing. It's mostly how the structure of it, like how its slopes are, and also how much surface area is there, and how close it is to the surface. So it can be in either one of these types, but it depends on how close they are to the where you have more photosynthetic activities.
Thank you.
Is there any international treaty for EZ zone? Because our fishermen, goes across the river and ocean, they will be caught and they will be taken in Sri Lanka or other borders to explore. For scientific studies, it is allowed to go and study everywhere, or is there any exclusive zone international trade.
You cannot go to another country, see easier and collect data without their permission.
Okay.
So that you always need to do. And in case of fishermen, because it's a very common happening in, for example, between Sri Lanka and India, a lot of fishermen going back and forth. This is a common problem. There is a Coast Guard always monitoring, putting them back. And as far as I know, I probably don't know whether there are such treaties available between the countries, but this is a very common problem, and these Coast Guard usually catch these people and then send them back.
Okay.
It's because overfishing and the overfishing is a big issue.
That was fascinating. With regard to the slides, the potential subterranean oceanics, there has to be a way to connect them with what's happening on the land, right? Because if you've got, let's say, in Kerala and other places, you've flagged potential huge slides, and we know there's a lot of deforestation, and and if you have changes in the monsoon patterns, increased rainfall, for example, or unseasonal rainfall, you will get a lot of flooding and a lot of wash off. So are these data being integrated, the oceanic data and the land data?
There are certain cases where that has been done. But for example, these particular areas where we think these landfills are mostly caused by high sedimentation rates. But in the past, because currently we don't have a monitoring system to see what is ongoing. So if there is a high rainfall season, how much is deposited coming into the ocean? We don't have such monitoring capability. So what we know is, okay, we see these past examples of slides. We know that high sedimentation rate is the reason. So we can actually use these, collect these sediment samples and actually predict how monsoon changed. Whether it was stronger during certain periods or less during certain periods. And these periods are not yearly, these are centuries or even thousands of periods.